Okay, good morning in Switzerland and good evening in Japan. So welcome to the 7th round of EPFL CIS-RIKEN AIP joint seminar series. So I'm Masashi Sugiyama, Director of RIKEN AIP. So it's my great pleasure to introduce our speaker today, Mikhail Siriotti from EPFL CIS. So he is currently an associate professor in EPFL, and he got PhD in physics from ETH Zurich in 2010. Then he spent 3 years in Oxford as a junior research fellow at Merton College. Then since 2013, he leads the laboratory for computational science and modeling in the Institute of Materials at EPFL. So he had many good awards, like including IBM Research Forschungs Prize and Volker Hein Young Investigator Award and ERC Starting Grant, something like that. So today he will be talking about nice title. So representing atoms clouds, the foundations of atomic scale machine learning. So that sounds a very exciting topic. So okay, so Michele, so now stage is yours.
Thank you very much, Masashi Sensei, and thanks everyone for joining. So let me start sharing the screen. Yes, so as Masashi Sensei mentioned, I'm going to try to do something a little bit different from the presentations that I usually do, that just present a broad overview of the activities in my lab. And I want to focus in particular on some more conceptual work that we have been doing in trying to understand the process of representing atomic structures as the input of a machine learning scheme. And I think that these given that at the end of the day we treat molecules as clouds of atoms, might also be relevant to other branches of geometric machine learning. So I hope that this will be interesting to this audience, and I hope that you will be able to give us some feedback as to whether this is also relevant for different domains of application. So before I start, I want to put this a little bit in context of my own domain of application, which is the modeling of materials and molecules at the atomic scale. So I really want to give some kind of historical perspective, and you know, with some paperback from the 50s, in general, the idea of modeling atomic systems on a computer has been based on the attempt of describing the interactions between the atomic components, usually with fairly simple functional forms that reflect the physics of interactions between atoms. So, you know, you may recognize some kind of electrostatic term, some kind of London dispersion, and some kind of harmonic terms that describe the chemical bond. Essentially, the idea was that by modeling on a computer the interaction between the atomic constituents of matter, you would be able to infer the macroscopic behavior that is relevant if you want to build a plane or a transistor. And actually, later on, somehow, with a combination of the increase in available computer power and the development of more efficient approximations to quantum mechanical theory, it has become possible to predict the interatomic potential, so the interaction between the atoms or the microscopic properties of matter, as we say, from first principles. So without any link to experimental observations, but just by solving the fundamental quantum mechanical equations that describe the interaction between atoms and electrons. So the problem is that even with the increasing computer power and with the availability of more sophisticated approximations, this is very time consuming. And so essentially this process of solving the quantum mechanical problem to link the structure of a molecule described by the position of the atoms and their chemical nature, so where the atoms are and whether they are carbon, hydrogen, or oxygen. So rather than solving the quantum mechanical problem to determine the properties that we want to compute, people have started using data-driven models to predict these properties based on a limited training set that is obtained by solving the quantum mechanical problem. Now, something that I will touch upon is the fact that even though the interatomic potential, so the stability of a molecule or a material, is one of the central properties to look for, given that it's what will determine which configuration is more stable and therefore likely to be observed in an experiment. There are other properties that are very useful to know, and here I'm giving as an example the electron spin distribution. So this is a simulation of an electron injected in a box of water, which is relevant for a number of electrochemical processes and radiation damage. There are many processes for which this is an interesting problem. And you don't only want to know how the atoms will move around, which requires knowing the interatomic potential, but you also need to know where the electron is, which requires being able to describe the probability density of finding the electron, which is a field in R3, so a more complicated property than just the energy, which is just one scalar associated with the entirety of the structure. So this has consequences from the point of view of the kind of machine learning models that we use, because we don't only need to be able to describe scalars, we also need to be able to describe vectors, tensors, fields, and so on and so forth. And I will try to show you examples of how these need to describe properties with a complicated algebraic structure affect the choices that we make in the machine learning schemes that we use. So even though I will focus mostly on the fundamental mathematical aspects behind this effort, in particular on the problem of mapping the Cartesian coordinate of the atoms to abstract feature vectors that are those that are actually used as the inputs for machine learning. So even though I will focus on these, I want some kind of to brag, perhaps, or in other terms, to convince you of the fact that for this domain, atomic and chemical and materials modeling, machine learning has really been a godsend, and there are a number of different difficult problems that are already being solved using a machine learning based surrogate model of quantum mechanics. And so this is the kind of glossy press overview of what we have been doing in this field. And so, for instance, we have been able to predict the thermodynamics, so the relative stability of different phases of water at finite temperature. So this is actually an extremely challenging problem, because not only the electrons behave quantum mechanically, but in water also the hydrogen atoms behave quantum mechanically. So this is a really, really difficult modeling challenge. And machine learning potentials that predict the energy and the forces between atoms have been absolutely invaluable as a tool to be able to address these questions. We have also been able to look at matter in more exotic conditions. So, planetary science, you often need to understand how matter behaves in conditions that are very hard to reproduce on the Earth. And this is a field for which atomic scale modeling has been super useful, because basically you don't need to recreate on the Earth the pressures that you find at the core of Jupiter. You can do a simulation with high levels of quantum theory, and you will be able to get very precise understanding on the behavior of matter in these extreme conditions. And machine learning also here has really allowed to push the boundaries of what can be done in modeling matter in extreme conditions. So I was mentioning the possibility of describing properties that are more complicated than a scalar, and I would have many examples here, but one example I wanted to show has to do with describing the polarizability of molecules, so how molecules respond to an applied electric field. And polarizability is a tensor. And so in order to be able to predict fully the behavior of a molecule when it's subject to an electric field, you need to predict tensors, which is very interesting from the point of view of how a machine learning functional form has to take care of fundamental symmetries. And last example, just again, really this is kind of a bragging moment, but more to emphasize how machine learning is really important for the field I work in. This collaborative work, we were able basically to understand the behavior of silicon in high pressure and describing both the structural and the functional transitions that are observed. So why is this? So this is basically just a statement on the fact that machine learning is important for atomistic modeling. But many of the people who have connected today probably are not particularly interested in modeling molecules. And the point I want to make here is that the way we regard molecules as the input for a machine learning scheme is actually very similar to the way objects are dealt with as the inputs of a machine learning scheme in many other domains, because essentially what we do is regard a molecule as I was anticipating, the collection of the position and the chemical nature of the atoms. So basically, from the purpose of the models that we build, molecules are just point clouds. And therefore, I think that a lot of the technology that we have been developing for molecules is also relevant in general for any kind of machine learning problems that is based on point clouds. And in particular, I will show you some results that might be interesting, which concern the description of molecules as graphs decorated with geometric information. So on a fundamental level, something that we have been working on very hard over the past couple of years has been trying to put some order and some systematicity in the way chemical structures are represented when used as the input for a machine learning model. And we have been so fixated with this that we have even developed a notation. Since I will be using it in this talk, I thought that I would spend a couple of minutes to introduce it so that you understand a little bit what is going on, since we are using a notation which is not entirely established. So essentially, the idea is that what we are trying to do is to describe feature vectors that represent a molecule or a set of atoms. And those of you who have some familiarity with quantum mechanics might recognize the RAC notation. Others might recognize notation that is used to describe scalar products. Essentially, we will use, since we will have a load of indices to deal with, notations in which indices are put at the PEDEX become very, very hard to read. So instead, we are using a notation in which the entity, the object that we're trying to describe is in the right side of the bracket. And in the left-hand side, we have the indices that enumerate the features. And the advantage of using this notation, which are really the reason why physicists use it to describe wave functions, is that it allows a very high level of abstraction. So you can really understand the right-hand side as a vector in an abstract Hilbert space. And then the indices on the left-hand side just as enumerating the features that you find when you project these abstract vectors on a particular choice of a basis function. So this is very useful because it allows you to separate the fundamental nature of a representation. and this would be like, in quantum mechanics, which state the system is in, from the specifics of how you implement which basis you use to describe your abstract vector on a computer to do calculations with it. So essentially, it will help us focus on the deep nature of representations without getting too much bogged down on the implementation choices of which basis you use to compute a representation in practice. And just to give you a few sort of patterns that you will see occurring, which again are very familiar for those of you who have done some quantum mechanics, you can describe a change of basis. So the same object, here I'm describing the molecule A, I might be describing it on a certain basis, and here the indices are enumerated by a label Q. And then I might choose to instead describe it on a different basis, and the change of basis is basically the scalar product of this vector with a vector that contains the coefficients. Well, actually, this is a matrix that describe the change of basis. Also, if you want to compute a kernel, kernels are also objects that very much like wave functions in quantum mechanics induce a Hilbert space that is not necessarily known explicitly, but you can but can be approximated with a kernel trick, basically. And the construction of a kernel is basically a scalar product in which you sum over a certain index, and if you use a complete basis, the value of the kernel doesn't depend on the basis that you choose to expand your feature vectors that describe a molecule. Also, I will use a lot linear models because they help a lot understanding the nature of these representations. So something that you will see a lot is me telling you, if you build a linear model on this representation, then this representation actually corresponds to this physical model. So I will use linear regression as a tool to understand the nature of the information that is being embedded in a specific choice of representation. And also a linear model is written very naturally using this Dirac notation because it's a scalar product between the feature vector and a vector of weights. So why are we going through this all this pain and all this effort? Well, one reason is that in my field there has been an incredible explosion of competing frameworks to represent molecules. And I mean, I'm an editor for one of the journals in my domain, and I receive at least a couple of papers a week that propose a new way of describing a molecule to then do machine learning with this description. So I think it's very important to understand whether these new frameworks have something fundamentally new, or if they are just, and perhaps this is, not just, perhaps it's something which is in practice very useful, but they are just a different choice of basis to represent the same object that everyone else has been using. So it is sort of a phylogenetic tree. We try to put some order in the state of the art for representations for chemical machine learning from last year. And actually, we are classifying different frameworks based on how one goes from the Cartesian coordinates of the atoms, basically a point cloud description, to a symmetrized representation that incorporates, permutation, translation, or rotation invariance. And actually, when you think about it, there are a few requirements that make very much sense and that have been incorporated in pretty much all of these frameworks. And some of these requirements seem to be pretty obvious. So for instance, you want the mapping between structures and features to be complete. more perhaps mathematically precisely, we want this mapping to be injective. We want that if two structures are distinct, they should be mapped to different points in feature space. Now, as we shall see, this is not so obvious if at the same time you ask for your mapping to be symmetric, meaning that if two molecules are the same and they are related just by some trivial rigid translation or rotation or changing permutation of the labels that we associate with the atoms, then these should be mapped to the same point in feature space. And this is, of course, it's very useful because it means that your machine learning model will be automatically invariant to these fundamental symmetries. But actually, as we also shall see, this makes it not so obvious to make sure that the mapping is injective. Then you usually want the mapping to be smooth. So if you move an atom smoothly in three-dimensional space, the trajectory in feature space should be smooth. And again, this is just because these reflect some fundamental properties of the structure property mapping from a quantum mechanical point of view. And something which is perhaps a little bit less obvious, but it's very important to get machine learning models that are transferable, is that the mapping is additive. And with additive, I mean that very often in molecular modeling, you write your function of the coordinates of all the atoms in a molecule as a sum of terms that correspond to atom-centered environments. So basically, the total energy of a molecule will be decomposed as a sum of contributions, each associated with one atom and its neighbors. And actually, if you make these ansatz for the target that you're trying to predict, this also implies that if you're building a linear or a kernel model, your features or your kernels must have a specific additive form. And this is actually very useful because it's what allows you to have a kind of a divide and conquer structure in the model, which means that you can train the model on simple structures and then make predictions on something which is much more complicated and potentially more interesting for applications. So this kind of Lego-like, Lego brick-like nature of the model is a consequence of making an additive ansatz for the target. So how can we go about and build symmetric representations that fulfill as many as possible of these requirements? And how can we do this in a way that doesn't rely too much on particular choices of basis functions and on the details, basically? So the starting point is the set of the chemical nature and the Cartesian coordinates of all the atoms in the system. Now, this is a perfectly fine description of my molecule. It's complete and smooth, but it's not symmetric. If I just change the order by which I list the carbon atoms, the Cartesian coordinates seen as a 3 times an atom vector matrix change. And then your machine learning model will have to learn about permutation invariance. And again, this is, of course, something which is very well known in general in the problem of machine learning models for point clouds. So what we do here is that we start by sorting out this permutation invariance issue. And we do this by describing our structure as a field, as a density, basically. So we put Gaussians or some kind of localized function. This might even be infinitely peaked Dirac distributions. And you see that, you know, if I give you this 3-dimensional field with these peaks, you can still very well identify where the atoms are. But now you cannot tell whether this is carbon atom 1 or carbon atom 166. And so we have basically obtained a description which is fully invariant to permutation of atoms of the same kind. And we use basically different channels. It's kind of a one-hot encoding in a certain sense to describe the chemical nature of the different atoms. Now, this is not invariant to translations because this is a function over 3. And if I rigidly translate my structure, this becomes a different function over 3. So the next step is making this description invariant to rigid translations of the molecules. And we do this by taking tensor products of the density, basically evaluating the density at 2 points and summing over the translation group. And if you do this, since the density is built as a sum of Gaussians centered on the atoms, you end up with a description of your structure, which is a sum of Gaussians centered on atomic pairs, because basically this integral will amount to a convolution of 2 Gaussians. So with this symmetrization, we achieve 2 goals. First, we get a description of the structure that is invariant to translation, because we have just summed over the translations. And second, we get a description of the structure as a whole that is expressed as a sum of atom-centered terms. So an additive decomposition emerges as a natural consequence of symmetrizing over translations. Now, even though we made the representation invariant to translations, it is still not invariant to rotations. So what we can do next is to obtain a rotationally invariant description by integrating over rotations these atom-centered pair density. And if you do that, you can imagine, I have this density centered on an atom, I integrate over all possible rotations. What I will obtain is some kind of smooth histogram of the distances around the central atom, which is, of course, invariant to rotations, but clearly is not containing all the information about the relative position of the different atoms in this environment. So what you can do is then build a tensor product of 2 of these densities, integrate over rotations, and this will give you something which depend on correlations between the positions of pairs of atoms. Those of you who have some familiarity with statistical mechanics will know that the way people have been describing liquids in statistical mechanics relies a lot on correlation functions of the atom density, and this is essentially what we're doing. We describe structures in terms of instantaneous correlations of this atom density. And you can generalize this construction to build correlation functions of arbitrary order, and this basically gives us a systematically improvable way of describing atom-centered environments. The more terms we include in the correlation, the more complete our description becomes. And actually, you can show that this hierarchy of correlations provides a complete linear basis to regress any function of the coordinates of the atoms within an atom-centered environment. So this does not only give us a complete description, but gives us a complete linear basis to regress any function of the coordinates of the neighbors of the central atom. And this is something which is has a very long-standing tradition in atomistic modeling. So we write the potential as a sum of pair terms, 3-body terms, 4-body terms, and so on and so forth. And basically, the vast majority, if not the totality, of descriptions that are used in machine learning for molecules can be regarded as a projection of these density correlation functions on a specific choice of basis. Now, I want to give some kind of a concrete example of how this works in practice. And I will do this with the smooth overlap of atomic positions, which is one of these representations that has been introduced in 2013. And I will try to show you how it can be obtained. So this is a representation that is defined and is constructed basically by expanding the atom density in a basis of radial functions and spherical harmonics. And I will show you how basically this is just one possible way of describing an object which is a pair correlation of the atomic coordinates. So the starting point is the set of interatomic distance vectors. And the objective is to describe not so much the entire structure, but an atom-centered environment. So I sit on an atom and I want to describe the relative position of my neighbors. So the first step is to move to a description in which this neighborhood is described with a neighbor density. And the reason for doing this is that now we don't have to worry about permutation, symmetry, and the order by which we list the neighbor of the atom. And still, this is a perfectly fine, complete description of the atomic neighborhood. But then we want to make this invariant to rotations. And what we can do, for instance, is build a 2-point correlations of this neighbor density, meaning that basically I will describe my environment by evaluating the density at 2 different points, x and x prime, and then integrating over all possible rotations of my molecules. So this you could regard a little bit as data augmentation, right? So rather than describing the molecule with a single orientation, I integrate over all possible orientations, and therefore I get a description which is invariant. However, since I'm evaluating the density at 2 points, I actually have information on the relative position of 2 atoms. So we could rewrite this expression as the integral over rotations for a single density evaluated over a stencil, which is defined by 2 distances and 1 angle. So if we take the sharp Gaussian limit of this object, what we have actually is a sum over pairs of neighbors of delta functions, delta distributions, since I'm speaking with people with a more mathematical rigor than the audience I usually speak to, is basically a sum of delta distributions that characterize the set of distances and angles between pairs of neighbors. And if we build a linear regression over this structure, over this representation, what we have is basically a fully symmetric 3-body potential. So a 3-body, so basically a function of the coordinates of 2 neighbors of each central atom that we can use as the basis to expand a model of the atomic properties. So are we actually summing over rotations explicitly? Well, actually we are not. And what we do instead is pick a convenient basis to expand the density. And nothing is changing here. This is really, if we use a complete basis, this is just the same neighbor density expressed in a basis of radial functions and spherical harmonics. And now we have discretized this continuous density into a vector that is labeled by radial indices. And then for each radial index, we have L and M indices that describe the angular part of the distribution. And the advantage of using spherical harmonics is that the way spherical harmonics transform under rotations is very well understood. They form an irreducible representation of O3. And so you know that if you rotate your molecule, the spherical harmonics basis will rotate in a way that is determined by Wigner matrices. And so when you try to write the rotational integral of the 2-point correlation of the density, this, this term that will give us a basis to express 3-body functions, you actually can use the orthogonality of Wigner matrices to express this 3-body function as a discrete sum of the terms of the expansion of the single density. So essentially now we have something which is entirely, in the complete basis limit, is fully equivalent to what we would have obtained by data augmentation and summing over all possible rotations. We obtain it just with a discrete sum over a discrete set of features for my molecule, and more specifically for my atom-centered environment. So using spherical harmonics is not only useful to get a closed form for the rotationally symmetrized features to regress scalar functions, but it's also very useful, even more useful, I would say, if you are interested in learning properties that are not scalar, but have a tensorial or vectorial nature. So, for example, if you want to predict the dipole moment of a molecule, that's a vector, and it's a vector that should rotate covariantly with the atomic coordinates if I rotate the molecule. So this vector will be described by 3 Cartesian coordinates. So it means that what I'm trying to do is basically build a model for the x, y, and z coordinates of this dipole moment, and in particular, the contribution coming from the I-centered environment. So if we build a linear model for this, I maintain that what we need to do is build feature vectors that are not only tagged by a feature index, but also by a geometric index that basically tells me whether I'm regressing the x, the y, or the z component. And the linear regression model should have weights that only depend on the feature index and not on the geometric index. So if we build a model with this structure and we ask ourselves how the prediction of the model would change if I rotate my molecule, then basically, if we can build features that under rotation transform like the application of a rotation matrix, we will get a prediction that basically transforms like a vector should transform. So basically, we get an equivariant model. So this fundamental idea underlies all the equivariant models for machine learning properties that are not scalars. And actually, the nature, you can use them, for instance, to build machine learning models for dipoles, so this very application. But more in general, if you want to do this for any tensorial property, you need to delve into SO3 group theory, and you need to regress, to build features that transform like spherical harmonics, basically. And this is something that you can incorporate very easily in this framework by basically decorating the integral that we build over neighbor densities with a set of spherical harmonics that will give basically a basis to expand the geometric part of the target. Now, what is very nice, and actually this draws a very deep connection to all of SE3 equivariant machine learning models that are out there, the fact that the machine learning exercise must be compatible with SO3 group symmetries puts very strict constraints of what you can do. You cannot just take features that transform like spherical harmonics of order lambda equal 2 and stick them as the argument of an arctan over a loop. You can't do that because that would break the transformation properties of SO3 that are basically linear transformation properties described by Wigner matrices. And so it turns out that this algebraic structure, so the fact that you build features that transform like angular momenta or spherical harmonics means that the only thing that you can do to build new features starting from features is some kind of Clebsch-Gordon iteration. So basically is taking two equivariant of lower order, essentially an equivariant that describe new neighbors, and a density expansion. This is just the coefficient of the density expansion, NLM, just written in a way that highlights their symmetry properties. And you combine them with Clebsch-Gordon coefficients that are the coefficients that basically give you the way to recombine irreducible representation of SO3 to obtain new irreducible representations. And this gives you a recipe to increase the body order recursively in an efficient way. Now, the issue with this is that every time you do a body order iteration, you increase, eventually exponentially, the number of features that you have to deal with. And so what we propose is that you do some kind of feature selection or contraction. Right now, we are just doing PCA, but the idea can be applied much more generally to keep the complexity of your featureization under control. But there is actually very little more that you can do. You just can't apply an arbitrary nonlinearity unless you restrict yourself to invariant features. Those are the only ones that can be sticked into a ReLU. And what is nice in this approach is that you can build systematically improvable linear basis to expand molecular properties. So as you increase the body order, you get higher and higher descriptive power using linear regression. So this is basically just linear regression. And of course, if you have a small amount of training structure, linear regression with good features can do better than a fancy neural network scheme. But what I want to stress here is that actually this construction gives you a way of understanding what are the pieces of information you are incorporating into the representation. Given that I'm saying that in a certain sense, different representations are equivalent, it becomes interesting to try and understand a little bit better what are the limits of how to compare different representations that have the same body order, and if there are reasons to pick one body order over another in the construction, if we can ever stop. And so one first thing I want to show you is a very simple idea to compare two different choices of basis to understand if we are losing information. And the idea is very, very simple. Basically, if we have two different featureizations, so we are describing the same objects using two different sets of features, the very simple idea is that what we can try to do is regress linearly the one set of features using the other as the input and measure the error that we are making in doing this linear approximation. And we can do this in one direction or in the opposite direction. And by comparing the error that we're making in the forward and in the backward direction, we can get some information on the relative information content, at least the part that can be embedded linearly, between the two representations. And here I'm showing a comparison between SOAP, this framework that uses a systematic set of spherical harmonics and complete radial basis, and Bell-Parinello symmetry functions that instead use functions that are optimized kind of more heuristically. And when you basically you have different limiting cases when you do this exercise in the forward and the backward direction. So if the error is 0 in both directions, it means that the two features encode the same amount of information. If the error is large in both directions, it means that in a certain sense, the amount of information that is encoded is complementary. So probably you should use the two feature sets together. And if the error is small in one direction and large in the other, it means that one set of features is objectively more informative than the other. And what we get here is that the two feature sets are roughly equivalent, but SOAP, given that it uses a systematically improvable basis, tends to have 25% more information retained than these more heuristic basis functions. So on a more fundamental level, I think it's very interesting to ask ourselves whether these representations are complete. So can we fully describe a molecular structure or point cloud using, for instance, just distances? So it's very well known that if you use the unordered set of distances between the two sets of points, you have an incomplete description. So you can build two tetrahedra where the set of distances is the same, but the tetrahedra are different. And actually something which is less obvious and that we figured out a couple of years ago, is that if you use these atom-centered descriptions, even if you use distances and angles to describe your neighbors, which, hand-wavingly, you might expect to give you enough information on the gram matrix to be able to reconstruct the environment, you actually can find structures that are degenerate. So basically, you can find pairs of structures that have the same set of distances and angles, which means that you can find pairs of structures that cannot be discriminated by representations that use distances and angles. And actually, we found also representations that are degenerate when you use the four-body descriptors. And actually, this has an impact on machine learning models in the sense that if you use low-body order descriptors, even if you feed them to highly nonlinear models that basically can incorporate effectively higher body order correlations, you find the kind of saturation in learning that is indicative of an incomplete description. This actually also has consequences when it comes to how point symmetries are incorporated in the model. For instance, if you look at the derivatives of the features with respect to atomic displacements, basically the Jacobian of the mapping between Cartesian coordinates and the features, you can find that there are directions, high symmetry directions, over which the Jacobian of a symmetric set of features must have zero singular values. And the problem is that when you have degenerate pairs of features, of structures, if the two pair of degenerate structures get very close together, then you also get some spurious singularities in the Jacobian. And this is relevant because when you try to learn, for instance, the energy of a molecule, the derivative of the energy is the force. And so if you have a symmetric structure, the force on the atom along a symmetric direction must be zero because of symmetry, because if the structure is symmetric, deformations in two directions lead to structures that are identical. But if you have structures that are not symmetric, then the gradient, the force is not zero, and the gradient of the features shouldn't be zero. Now, if you have features that are degenerate, you have spurious zeros, which means that we cannot learn non-zero forces for these structures no matter what. And this is actually very interesting in order to understand the limit to machine learning models that are based on low body order descriptors that are used by and large by the majority of my community. This is actually also very interesting when it comes to incorporating more sophisticated symmetries. So if you try to learn Hamiltonians that are basically describe the electronic structure of a molecule, you have very subtle rules that are actually taught in undergraduate chemistry, that are molecular orbital theory, that tells you that for a molecule that has a certain point group symmetry, its electronic states must basically obey the symmetries of D6H, of the six-fold symmetry group. And what is very nice is that models that incorporate just the basic permutation and rotation symmetry incorporate automatically also all of these point group symmetries, which helps a lot when you're trying to machine learn the electronic structure of molecules. Now, I want to conclude the last section of my talk. I want to conclude by showing some very, very recent results, basically, which appeared on the archive tonight, in which we try to see how all of these considerations extend to graph convolution schemes that are also very, very popular in machine learning of molecules and are, of course, also very, very popular for point clouds in general. So the vast majority of schemes that are used for molecules rely on describing molecules as a graph in which atoms are nodes and the edges are the interatomic separations that are decorated with the distance between the atoms. And the way graph convolution is implemented for molecules and for point clouds in general involves basically looking at the set of the multiset, to be precise, of neighbor labels and distances around each atom, and then build some kind of function that in the most general sense corresponds to a hash of this multiset. Then, after you have built these functions, then you can use them to describe the nodes, and you can iterate the process. So this is called the Weisfeiler-Lehmann test. And if you apply it to discrete graphs, it's very well known that there are graphs that are different, but they are indistinguishable by this Weisfeiler-Lehmann test. But actually, if you consider point clouds in three-dimensional space and you decorate the edges with the actual geometric distance, you basically add a geometric dimension to the graph theoretical problem. And as far as we know, this far, nobody has been able to find molecular point clouds, molecular structures for which the distance decorated graph is the same. And actually, all these degenerate structures that I have talked about before for atom-centered descriptors are very easily separated by graph convolution network, which some have interpreted as one of the reasons why GCNN work so well for molecules. And actually, the same student who had found this counterexample for distance and angle atom-centered descriptors has been able to find a geometric construction that creates point clouds whose distance decorated graph are basically, you can find pairs of these structures that are indistinguishable based on a Weisfeiler-Lehmann test, first order Weisfeiler-Lehmann test. And basically, you can build three-dimensional structures, three-dimensional point clouds that have this degeneracy. And you can build plausible molecular geometries. So these are structures that correspond to little clusters of water molecules. So very reasonable structures with energies that are, structures that are comparatively stable. And these two structures cannot be told apart by the standard first order graph convolution neural networks that are used in chemical machine learning. And this means that if you try to build a machine learning model for water clusters, which is a very reasonable exercise, the cross-validation error on a trained set of more or less randomly generated structures decreases with the train set size, so everything seems to be working fine. But if you try now to make predictions for these pairs of structures, the predictions are bound to be the same because they cannot be discriminated by these first order graph convolution neural networks, which basically sets a limit to the accuracy that can be reached by this family of models. Now, if you use SOAP features that also incorporate information on the angles in describing an atomic environment, then there is no problem, and you can learn and can make predictions for these degenerate pairs because they are not degenerate if you consider the angles between the atoms. And this actually also means that last generation graph convolution neural networks that incorporate information on the angles or on the directionality of the connection between the atoms are immune to this problem. So to sort of wrap up and summarize so that I leave a few minutes for your questions. Machine learning is very useful for atomistic modeling, and I think that some of the, the culture of fitting potentials that have been prevalent in this community since the 50s gives us a perspective for looking onto the problem of machine learning that might also be interesting, perhaps, I hope, for other domains. for this domain, considerations of locality, symmetry, and equivariance are really central and have been incorporated into models since the very, very early days of using machine learning for materials and molecules. And, leads to this perspective of looking at the machine learning problem in terms of the geometry of a point cloud, which might also be interesting perhaps for looking at autonomous driving, shape recognition, and so on. I think that this effort to systematize the construction of atom-centered representations can be very useful. Something we are trying to do is to see if we can also use a similar idea to systematize the construction of message passing architectures, because I don't know you, but when I read a paper about message passing in my field, I have a very hard time understanding if two different papers are doing something different or they are doing just the same thing, just using a different notation and dressing up the problem in a slightly different way. So with this, I want to conclude, but not before I thank the members of my group here in pre-pandemic and post-pandemic attire. Tell you that you can find most of the code that we have been developing to do these things on GitHub. And if you want to download the slides, I have made a tiny URL so that you can find them easily. And I believe that a video will be uploaded to the RIKEN pages shortly after the talk. So thank you for your attention, and we'll be happy to answer your questions.
Yeah, thank you very much, Michele, for the great talk. So now the session is open to the audiences. So if you have any questions, please write them in the Q&A window, or you may directly unmute your microphone and speak. So then, as a privilege of the chairperson, let me first ask a question. So I think today you didn't talk about practical implementation part. So in practice, how can you compute those expressions in computer, and also what's the maximum size of the input you can handle in the current implementation?
That's excellent question. So in practice, all the major, not all, but vast majority of the implementations relies on expanding the neighbor density in spherical harmonics and then doing discrete, basically matrix multiplications to build the higher body order terms. And in practice, thanks to the fact that this is an atom-centered and additive scheme, you can easily go to billions of atoms with some implementations. It depends on how thorough you want to be and how thorough you need to be in truncating this expansion. And this is one of the open questions that we're trying to address. So we know that on a fundamental level, three-body descriptors are not enough, but in practice, people have been doing pretty well with them. So understanding this is one of the open questions and something that I believe that getting the interest of people with a better mathematical education than we do would be very, very interesting. So
yeah, thank you. Now we have actually many questions in the Q&A window. Can you see them?
I see them. So does your method have some kind of spatial discretization parameter from François Bérenger? In a sense, yes. The spatial discretization is more a resolution parameter, if you wish. So you can set the width of this Gaussian density that you put on the atoms, and this is reflected in the number of terms that you need in the expansion. Another very important parameter is the cutoff distance. So how far should you go in describing atomic neighborhoods? And this is another thing on which we're working on, but this is an entire other talk, and I didn't have time to discuss that. But so there are two parameters basically that are most important: the resolution that is set by the Gaussian width, and the scale and the length scale of the interactions that is set by the cutoff. So I hope this answers this first question. In which of your papers do you introduce your rotation translation invariant representation by atom-centered Gaussians? Okay, so basically what I suggest that you do is that you look up this review, because this is the interesting aspect is that these representations have been around for 10 years, but people didn't realize how closely related they were until very recently. And in this review, it's actually 2021, it's from last year, it's a ChemRev. I think it's a good starting point because we try to give a pedagogic overview of the framework, and this is also written together with Christoph Ortner, who is an applied mathematician. So it's also as watertight as it gets for a paper published by me. Is there any relationship between atomic machine learning and quantum many-body systems or tensor networks in physics? Probably yes. So it's one of the challenges that I find personally is that different communities use a very different language. And so, for instance, I would be very interested, you can also send me insulting emails after the talk if you don't want to do this publicly. I would be very interested in knowing if, with this graph convolution stuff, we are saying something that is very obvious to the point cloud geometric machine learning community, because it's very difficult to decipher a paper from a different community. So I do think that there are many connections and many possible synergies between different fields. I think that these kind of events are a good way to establish a line of communication, like the Kremlin red phone, and try to understand what can be transferred, what is already known, and what is non-trivial, what are non-trivial problems on which we may work together. Recently, there were claims that LSTM based on sequence representations can still be useful to ML on molecules. What does LSTM mean? I'm sorry.
It's like a recurrent neural network called long short-term memory.
Oh,
maybe this should be discussed later offline, or?
Yeah, they seem different. It's a very interesting question. I don't know, and part of the reason I don't know is that it's really hard to, and I'm sure that it's also hard for people from that community to understand what we're doing in these papers. So yeah, this is something that most definitely would be very interesting to discuss offline.
So I have one more short question. So in standard computer vision tasks, so we also care like translation and invariant, rotation invariance and things like that.
Mm-hmm.
And they are often like, we don't really do anything special, but we just augment data and we just grow the number of data points extremely. Yeah. But still, like, we can train a deep network easily if we have a huge number of data points. Yeah. So what happens if we just apply this naive idea to your case? And does it really fail, or?
So, I mean, there are two aspects. So one is if you don't have to, why doing it? So if you can handle a smaller training set, it's useful because you can, you reduce the cost of training. You can do more things that are interesting. So I see a information efficiency argument for trying to make the model equivariant by design rather than by data augmentation. And the other aspect is that we very often worry about derivatives. So we really want, in a symmetric point, we want derivatives to be exactly zero. So you will need a huge number of augmentation points. If you incorporate equivariance in the model, these derivatives are exactly zero. If you incorporate them by data augmentation, they will be close to zero. but it will be very hard to converge these to be exactly zero. So these are the two main reasons why, but you know, broadly speaking, yes, data augmentation works also for this domain.
Yeah, thank you very much. But the second point is really important, I think.
Yes, I agree.
Now Volkan is back, and do you also want to ask a question?
Not at the moment, sorry.
No problem.
Thank you.
Okay, I think we had many questions already, and if you don't have any further questions, then that's the end of the session. So, okay, then, so please join me to thank Mikhail for his great talk today.
Thanks a lot. It was really, really nice.
Thank you, Mikhail.
So then let me briefly talk about the next round of the seminar. So today, 19th January, right? So then the next round, 8th round of EPFL CIS-RIKEN AIP joint seminar series is held in 16th of February by Chibin Zhao from RIKEN AIP. So we are looking forward to meeting you again.
Looking forward to it.
Okay, thank you very much. That's all for today. So please have a nice day in Switzerland and have a good night in Japan.
Thanks a lot. Bye-bye.
Thank you.
Bye-bye.